Hello, Namaskara. Welcome to Digital Learning by the Department of Collegiate Education. I am Manjunath CV, working as Assistant Professor at Government First Grade College CSPura, affiliated to Tumkur University. In today's session, let us try to understand what is probable error, how to find out probable error, and what is Spearman's rank correlation, its meaning and features. This is session number 6 of the chapter correlation analysis and the subject quantitative analysis 2. So let us straight away get into understanding what is probable error. Probable error is a statistical tool which is used to measure the reliability of value of Karl Pearson's correlation coefficient insofar as it depends upon the random of sampling. So we have tried to understand in session 4 and 5 how to calculate Karl Pearson's coefficient of correlation under the direct method and the indirect method, that is shortcut method or assumed mean method. Now, how far is this correlation valid? How far is it significant is what we will be trying to understand with the help of probable error. According to Weldon, probable error defines the limit above and below the size of the coefficient determined within which there is an equal chance that the coefficient of correlation simply calculated from other samples will fall. According to Weldon, probable error defines the limit above and below the size of the coefficient determined within which there is an equal chance that the coefficient of correlation simply calculated from other samples will fall. Now, what does this actually mean? How do we understand this? It means, for instance, we would have calculated the correlation coefficient. Let us assume the correlation coefficient to be 0.8236. So from that we interpret that it is a positive correlation and there is a strong positive correlation because the value is near to 1. Now, if we choose another sample from the same universe, that is from the same sample size, and if we conduct or check the correlation again, the correlation should fall more or less very close to whatever we have found already. So that more or less is defined as lower limit and upper limit. So R plus probable error is the upper limit and R minus probable error is the lower limit. For example, I said 0.82 was the correlation. If we add the probable error to this, which is being calculated according to a formula, let us say the upper limit will be somewhere around 0.86 and the lower limit is somewhere around 0.78. Then when we reconduct the test again within the same sample size and same universe, then the next time correlation should be somewhere between 0.78 to 0.86. This is what it actually means. If correlation is significant, then it will definitely fall under the lower limit and the upper limit. If correlation is insignificant, then there are chances that the correlation which we find out again may not fall between the upper limit and the lower limit. So here I repeat once again, it says probable error defines the limit above and below the size of the coefficient correlation determined within which there is an equal chance that the coefficient of correlation similarly calculated from the other samples will fall. The formula for calculating probable error is as follows. Now the probable error formula is 0.675 into 1 minus r square divided by the square root of n, divided by the square root of n, where r represents the coefficient of correlation, n indicates the number of pairs of observations. The significance of probable error. Why calculation of probable error is actually important. Probable error of coefficient of correlation gives us two limits, which I already told you. One is the upper limit and the other one is the lower limit, within which the coefficient of correlation of series selected at random from the same universe is likely to fall. This implies that if we take another random sample of the same size n from the same universe of data from which the first sample was taken, the new value of correlation coefficient can be expected to fall within the limits of r plus PE and r minus PE. The upper limit is r plus probable error and the lower limit is r minus probable error. So let us try to understand these while we solve 2 to 3 problems on the basis of probable error. If the value of r that we have found out is more than 6 times the probable error, the existence of correlation is certain, which means the value of r is significant and important. So the next time when we conduct the sample test, generally the values will fall between the lower limit and the upper limit. But if the value of r is less than 6 times the probable error, then the existence of the correlation is uncertain, which means this correlation may not bear any significance. When the test is conducted again, the value of r may not lie between the lower limit and the upper limit. Now, let us look at how to solve problems on the basis of probable error. So what is probable error? It is a statistical tool which is used to measure the reliability. The major focus is on checking how far is this correlation reliable, identified under Karl Pearson's coefficient of correlation. So that is the main objective of probable error, to check the reliability of Karl Pearson's coefficient of correlation, which we have already found. So probable error, the formula is 0.6745 into 1 minus r square divided by square root of n. Now, as I said, there is an upper limit and a lower limit. I will come to this topic later. So initially, there is a problem here which says r is equal to 0.6, that is Karl Pearson's coefficient of correlation is equal to 0.6 and n is 64. Find out the probable error and determine the population correlation coefficient. So the solution is, let's write down the formula. Probable error is equal to 0.6745 into 1 minus r square divided by square root of n. So probable error is equal to 0.6745 into 1 minus r. The value of r is 0.6. So that is 0.6 the whole square divided by square root of n. The value of n here is 64. So probable error is equal to 0.6745 into 1 minus 0.6 the whole square is 0.36 and square root of 64 is 8. 8 8s are 64. That is equal to 0.6745 into 1 minus 0.36. 10 minus 6 4 and 9 minus 3 6. 0.64 divided by 8. 1 minus 0.64. So probable error is equal to 0.6745 into 1 minus 0.36 is 0.64. That is equal to 0.6745 into 8 ones are 8. 8 into 0.8 is probable error. And finally, the answer for probable error here is 0.6745 into 0.08, which is 0.05396. Right? So this is how we calculate the probable error. We apply the formula 0.6745 into 1 minus r square divided by square root of n. So this is the chances of getting probable error from the calculated correlation coefficient, which is r. So now we know that already our r is equal to 0.6 here. So the chances of variation of r, if it is significant, should be either within certain limits, that is less than or more than. So maximum, the lower limit of is equal to r minus probable error, that is 0.6 minus 0.05396, that is equal to 0.6 into 0. Minus 0, this is 0.5460, the lower limit, and the upper limit is equal to r plus probable error, that is 0.6 plus 0.05396, which is 0.65396. This is the upper limit. So now what do these lower limit and upper limit indicate? As we know here, the correlation is 0.6 and the sample size was 64. Now if we conduct another test, right, and check and pick the samples at random with the same sample size and the same universe, the probability of getting correlation should lie between 0.5460 and it should not exceed 0.6539. So that is what it indicates. There are chances of correlation which could be either less than 0.6 or more than 0.6 within the limits lower limit and upper limit. The lower limit is 0.5460 and upper limit is 0.6539, which means the correlation should fall somewhere between 0.54 and between 0.65. Now this is generally possible, and this is what generally happens if the condition is that if r is, the condition is satisfied only if r is significant. I repeat, this is possible only if r is significant. Now how do we identify whether r is significant or not? So to identify whether r is significant or not, there is a certain condition, and the condition says that, I erase this for reference, and the condition says, when is r significant? When, if r is greater than 6 times probable error, we mean r is significant. R is significant. And the same, if r is less than 6 times probable error, r is not significant. R is not significant. Now we have our r given in the problem as 0.6. So let us find out what is 6 times of probable error. In the question here, I will write it here, 6 into 0.05396, that is equal to 6 into 6, 36, 54 plus 3, 57, 21, 23, 250 plus 2, 32, 0.32. So the value of 6 times probable error is equal to 0.32376, and what is the value of r? It is 0.6. So since r is greater than 6 times probable error, our conclusion is that r is significant. So this is how we find out whether r is significant or not significant. Let me repeat the entire concept here. Now we have found out probable error, and we have set the lower limits and the upper limits. So according to the lower limit and upper limit, which is 0.54 and 0.65, if we conduct a test again here from the same sample size and the same universe, in that case the correlation coefficient should lie between the lower limit and the upper limit, which means the R should lie between 0.5460 and to a maximum 0.6539. Now when is this possible? Only if correlation is significant. How do we find out the significance of correlation? By applying the condition here. The condition says if value of R is greater than 6 times probable error, it means the correlation is significant. And if value of R, that is the correlation, is less than 6 times the probable error, R is not significant. R is significant means when you conduct a test again from the same universe and the same sample size, in that case the possibility is that R will lie between the lower limit and the upper limit. So in this question, our probable error is 0.05396 as we have got. So 6 times probable error is 0.3276 and the correlation is 0.6. Therefore, correlation 0.6 is greater than the 6 times probable error, that is 0.3237. Hence, we can conclude that R is significant. So this is the objective of identifying the reliability of Karl Pearson's coefficient of correlation. So I hope you all have understood. I'll have a just recap once again. We're going to find out probable error. What is the objective of probable error? To find out the reliability of Karl Pearson's coefficient of correlation. We have the formula for probable error. Accordingly, we find out the probable error. We find out the lower limits as well as the upper limits. And to conclude whether R is significant or not, we apply the formula and find out whether R is significant or R is not significant. Let us solve one more problem to understand and compute how to compute probable error, number one. Second, let us find out the lower limit and the upper limit. And finally, let us interpret what is the value of R. So we know that the value of probable error is equal to 0.6745 into 1 minus R square, that is correlation the whole square, divided by square root of n. From the given data, we know the value of R is equal to 0.75 and also that n is equal to 36. So let us apply our formula. Probable error is equal to 0.6745 into 1 minus R square. The value of R is 0.75 the whole square divided by square root of n, which is square root of 36. Probable error is equal to 0.6745 into 1 minus 0.75 into 0.75 is 0.5625 divided by square root of 36 is 6. So probable error is equal to 0.6745 and 1 minus 0.5625 is 0.4375 divided by 6, that is equal to 0.6745 into 0.0729 into 0.6745. So the probable error is 0.4917. This is the probable error. So we have found out the first part, which is calculating the probable error. Next, let us calculate the upper limit and the lower limit. Now let us look at the upper limit and the lower limit. the lower limit is equal to R minus probable error, which is equal to, the value of R is 0.75, 0.75 minus the probable error is 0.049, 0.049. Therefore, the lower limit is equal to 0.75 minus 0.049, which is 0.691. And similarly, let's find out what is the upper limit, R plus probable error, that is equal to 0.75 plus 0.049, that is equal to 0.799. This is the upper limit. So once we have found out the lower limit and the upper limit, we can say that the value of R would lie between 0.691 and 0.799, comma, the condition is if R is significant. If R is significant. Now we have put a condition that if R is significant. So let us find out the significance of R. So let us find out what is 6 times probable error. That is 6 into 0.049. 6 nines are 54. 5. 24 plus 5, 29. 2. We know that 6 times probable error is equal to 0.294. Now, if R, condition is if R is greater than 6 times probable error, that is, the value of R is 0.75, 6 times probable error is 0.294. Therefore, we can say that 0.75 is greater than 0.294. Hence, we can conclude that R is significant. We can conclude that R is significant. Now, what does this mean? It means if the same experiment is repeated, right, with the same sample size and in the same universe, there are majority chances that the coefficient of correlation will lie between the lower limit of 0.691 and the upper limit of 0.799. That is what we are going to interpret in the case of coefficient of correlation. So this is about probable error, how to find probable error. Second, finding out the lower limit and the upper limit. And finally, interpreting the value of R, whether it is significant or whether it is not significant. So I hope you all have understood the concepts thoroughly with the help of these two problems. Till now, we have discussed probable error. What is probable error? How do we calculate probable error? What is the lower limit and upper limit? What do they indicate? And finally, how do we interpret the value of R? Is correlation significant or is it insignificant in the test that we have conducted? So let us proceed further and look at what is Spearman's rank correlation coefficient. In the previous sessions, I have already told you all that Karl Pearson's coefficient of correlation is important while computing the correlation for quantitative variables. And now, when we have certain abstract variables or abstract characteristics or qualitative characteristics such as intelligence of the students, leadership abilities, etc., we cannot measure them in quantitative terms. Hence, these are subjective in nature, and hence the qualitative characteristics have to be ranked according to some particular order. We have to put them in a serial order according to certain ranks. Hence, in case of qualitative characteristics or abstract characteristics, we will use Spearman's rank correlation coefficient. Now, the first line says, when statistical series in which the variables are under study are not capable of quantitative measurement. We cannot measure them quantitatively in terms of numbers, but they can be arranged in a serial order or according to some ranks. In such situations, Karl Pearson's coefficient of correlation cannot be used. So this is when in 1904 a British psychologist named Charles Edward Spearman. I repeat, Charles Edward Spearman was a British psychologist who developed a method to measure the correlation coefficient between abstract characteristics or qualitative characteristics. For example, it could be beauty, intelligence, leadership abilities, etc. So this method is known as Spearman's rank correlation. We have three main methods under our syllabus for computing correlation. It is scatter diagram, Karl Pearson's correlation, and Spearman's rank correlation. Apart from that, we also have the method of least squares and few more methods to calculate correlation. So scatter diagram is a theoretical concept which graphically represents the correlation between two variables. The drawback here was that scatter diagram does not give a mathematical value to the correlation. To overcome this demerit or drawback or limitation of scatter diagram, in 1892, the British statistician, a British mathematician named Karl Pearson introduced his correlation called as Karl Pearson's coefficient of correlation, which gave a mathematical value to correlation. Further, under Karl Pearson's coefficient of correlation, values or characteristics which can be measured in quantitative terms are only used. So this was qualitative or plus points of Karl Pearson's correlation, and the demerit was that qualitative or abstract characteristics could not be measured. So this demerit of Karl Pearson's coefficient of correlation has been overcome by Spearman's rank correlation coefficient in 1904. So that's a brief introduction to the different types of correlation and Spearman's rank correlation coefficient. Now the formula for computing Spearman's rank correlation is as follows. R is equal to 1 minus 6 sigma d square divided by n cube minus n, wherein R is the rank correlation coefficient, D is the difference between the ranks, and n is the number of pairs of items. And this is calculated similar to Karl Pearson's coefficient of correlation, and here also the correlation should lie between -1 and +1. So dear students, please note when you solve problems and if you get the value of R as more than 1, that case it means your problem has been done wrongly. So the limits lie between -1 and +1. That is the range of correlation coefficient. Either it is Karl Pearson or it is for Spearman's rank correlation. The value of R should lie between -1 and +1. In Spearman's rank correlation, we come across three different types of situations. Situation A, when the ranks are not given and we have to assign the ranks. Situation 2 is when they have given the ranks directly. And situation number 3 is when ranks are given but there are repeated ranks in the given data, or when ranks are tied. For example, two students securing the same mark will get a tied rank. So the ranks repeated could be either 2, 3 or even more than 3. These are the three different situations: when ranks are not given, when ranks are given, and when the given ranks are repeated ranks. So what are the features of Spearman's rank correlation? Number 1, the sum of the differences of ranks between the two variables shall be 0. Second, Spearman's rank correlation coefficient is distribution free or non-parametric because there are no strict assumptions made about the form of population from which the sample observations are drawn. Third, the Spearman's rank correlation coefficient is nothing but Karl Pearson's correlation coefficient between the ranks. Hence, it can be interpreted in the same manner as Karl Pearson's correlation coefficient. So that's all for today's session, dear students. Let's have a small recap. We have tried to understand the concept of what is probable error, why do we calculate it, how do we calculate it. We have tried to solve two problems in this video session, and we have got an insight as to what is Spearman's rank correlation, what are its features, and when are we going to use Spearman's rank correlation coefficient. So I hope you all have understood this particular concepts. Thank you, students.